you're a reasonably small company, you're deploying certificates pretty much entirely for in-house consumption, then having an environment where this might be your only CA is probably a reasonable thing to do. Larger organizations are going to build an offline, standalone root CA. That computer is not going to be a domain member necessarily. It's going to be configured as a CA. It's going to be used to create the certificates for subsidiary CAs. And then, to be able to comply with security best practices, we're going to shut that computer down and put it in the closet. We'll take its hard drive out and put it in some other closet. But in this case, we're going to do a nice, simple enterprise CA scenario. So my starting point, of course, is going to be to install the software. So let me go to Add Roles and Features. Certificate Services is what Microsoft terms a role in this scenario. Roles are the important stuff. I might dedicate a whole server to it. Features are the ancillary benefits, the additional features I might use to help support the roles. I'm going to install it on Dallas Server 2. I'm going to deploy, there it is, Active Directory Certificate Services, ADCS. Do I want to include the management tools? Sure. Real world, I might prefer to just install the server components and put the management tools on a client machine, but in this case, perfectly sensible to include it here. Next question, do I want to put any features on this server? In this case, no. Of course, having chosen the client tools in the prior step, we would see if we scroll down inside of the remote server administration tools down here, we would see that we had chosen the client components for this, but that's already been accomplished. So we'll go ahead and click Next. As usual, Microsoft gives us a description of what Certificate Services is and does, why we might want to use it, IPsec, network access protection, EFS, email encryption, SSL, lots of good reasons for using Certificate Services. Clicking Next brings us to the opportunity to choose additional role services. These are add-on features of ADCS that fulfill a number of different roles. The centerpiece, of course, is the Certification Authority, the CA. That is the brains of the outfit. This is the software that makes certificates available. It fields requests from clients. It publishes a CRL, a certificate revocation list, a list of those certificates that have been banned from use for one reason or another. The next piece is the CA Policy Web Service, which in conjunction with the CA Enrollment Web Service provide the two edge servers, if you will, for certificate services. By which we mean these are servers that I might choose to place in a DMZ to give them exposure to the internet, principally because I want to do certificate tasks not only from inside of my environment, but sometimes from outside. So you can see in the description off to the right there, the CA, the Certificate Enrollment Policy Web Service, lets users obtain enrollment policy info, the rules about getting certificates, even if you're outside of the network. We're connecting in via the internet, and this server is waiting there in what's sometimes called the DMZ. You'll see Microsoft will sometimes call it the perimeter network. The Certificate Enrollment Web Service is another edge server. It sits in the DMZ, sits in the perimeter network. Its job to be the server that fields the requests to actually enroll for certificates, to say, hey, I want one of those certificates. Can I have it, please? The Certificate Authority Web Enrollment is actually a web application that provides an internal to the company user the ability to connect to this CA and issue a request for a certificate via a web interface. Alternatives would include calling the CA administrator and supplying details about the certificate that you would like over the phone. But in some environments, a self-service option is a good one, and the CA Web Enrollment form provides that ability. NDES, Network Device Enrollment Service, is all about assigning certificates to hardware gadgets that run your network, routers, switches, other devices, where I want to be able to encrypt the communication to those devices. Well, if I want to do that, it would be sensible to be able to supply a certificate for those computers to do that encryption, public-private key encryption. It's a neat technique. And lastly, something called an online responder. There have been challenges over the recent years with the amount of stress being put on certificate services, specifically with the number of checks to see if a particular certificate is valid or not. It's possible to offload some of that responsibility to another server by installing onto it the online responder feature, giving clients an alternative target to go check to be able to ask questions about whether a certificate is valid or not. In this case, I'm just going to roll out the top option, the Certification Authority. We're ready to install. I'll go ahead and click Install. deployment of certificates has been analogized sometimes to getting a driver's license from the Department of Motor Vehicles, or whatever they call your local driver registry facility where you are. You supply credentials to the DMV, and in trade they provide you with a document, something that binds your identity to information that is going to be identifiable by someone who wants to validate your identity, like a police officer. That individual trusts the DMV. The DMV has validated your identity. They trust that you are who you say you are. Therefore, the officer can trust that you are who you say you are by supplying that certificate. We're creating a somewhat similar environment here in certificate services. So having finished the installation, we do need to complete that configuration. We've installed the binaries, but we've not yet configured the details of how this server is going to work. So I'll click the link to configure ADCS on this server. It invites me to confirm that I am a member of appropriate groups that are relevant for the particular features that I want to install. In some cases, I need to be a member of the local administrators group. In other cases, I need to be a member of the enterprise admins group. Enterprise admins are by default a member of the domain administrators group of every domain in my Active Directory forest. And it's that credential that's required for some of the more sophisticated, some of the more broadly impactful features of ADCS. The deployment of my web services are putting technology in the DMZ in a way that's going to, if it's not configured properly, it's going to make my network more vulnerable. That's something that requires somebody with a fairly high level of privilege. On the other hand, if I'm creating a standalone CA that's going to apply to this server and it's not an enterprise CA, it's not integrated with Active Directory, I can get away with just being a local admin for that purpose. In this case, I'm going to do the work as domain administrator, globalmantics/admin. I'm going to click Next. Wants to know which role services I'm configuring. I only installed the one, so we'll choose the one that's appropriate. Having done that, we'll click Next. It wants to know which type of CA I'm using. And in this case, for my purposes, I'm going to choose Enterprise. Enterprise CAs, it does point out, need to be members of the domain. They're integrated with Active Directory. They will be making certificates available probably by way of leveraging the group policy feature of Active Directory. Clients will be able to call the domain controller and say, hey, could you help me find a certificate server? And the domain controller says, oh, sure, Dallas Server 2 is a certificate server. Go talk to that guy. Standalone CAs, you'll recall, is the alternative. Standalone CAs can be made offline, and that's one of the main reasons for choosing a standalone CA, is to have an offline route. Offline servers can't be compromised through any sort of a network attack. And because that server's sole goal is to be able to authorize the use of other servers, once that's been accomplished, it's a security best practice to take the root offline. Those of you that saw the first Mission Impossible movie, remember the secure computer that the secret agent needed to get into in order to save the day. That computer wasn't networked. It was a standalone root of a sort. They had an online root. I would have turned that computer off if it were me. But anyway, let me re-choose Enterprise CA and click Next. I've got my choice of a root or a subordinate. Subordinate CAs lie beneath some other certificate authority. That CA might be a root, or it might be yet another subordinate. It might be that a subordinate is 2 levels below the root, or 3 levels below the root, although that would be somewhat rare. A 2-tier or a 3-tiered scenario is fairly common, with a root at the top, and one or more policy CAs as subordinates to the root, each of which with different sets of rules for deploying different kinds of certificates in different sorts of ways, maybe in different regions of the world. And those policy CAs then enable the use of the issuing CAs, the ones that actually make available the certificates that are used by individual users and computers and services and such. So in this case, my first CA is going to be a root CA. Next question, where is the private key coming from? We identified that one of the major tasks of a public key infrastructure is managing the relationship between public and private keys. Public keys are shared broadly. Private keys are kept internally. The private key really is a local identifier of the individual who owns that key. To have the private key is to have a piece of information that makes it perfectly clear to someone that you are that user. So that information needs to be kept carefully guarded. But furthermore, if I decommission an old CA and move over to using some new CA, I would like to ensure that the idea of identity rolls from the decommissioned server to the new one. I don't want to have to recommission all of my certificates just because I changed certificate authority servers. This bit of interface provides that ability. I can either create a new key in a case where I'm creating a new CA from scratch. Perhaps this is an environment in which I've never had a CA. This is my first one. Alternatively, I can choose to reuse a key if I have one. Again, perhaps if I've decommissioned an old CA, I can take the existing private key from that certificate authority and import it into this one. I can pull that data in from a digital certificate, or if I've already imported that certificate, I can identify the existing private key on my system and say, yep, that one is me, that one is this server. In this case, this is a brand new CA, so I'll choose that topmost option to create a new private key. My next set of questions get very deep into the nerdy details of cryptography. And I encourage you to do outside reading on the technical details of how cryptography works. I filled in some of the basic details as we introduced this module. I filled in some of the basic details for you as I introduced this lesson. But you'll recall that the creation of a asymmetric key pair, a public and private key pair, requires the generation of a lengthy number. I get to choose how large of a key I want to use for those purposes. The larger the number of bits in the key, the more secure it is. On the other hand, the more processor intensive it is to encrypt and decrypt data using that key. The larger the key is, the more time it takes the certificate authority to generate a key of that sort. It's possible to generate a key of a size of 16,384 bits and spend a day to do it because it takes that much processing power to calculate the large prime numbers involved in that sort of an operation. Left of that is a choice of a cryptographic provider. A provider is a package of software to be able to perform all the operations that a CA does under the hood. Encrypting data, storing keys, decrypting data. We'll see that a cryptography provider may also provide one or more of what are called hashing algorithms. And different providers take different approaches to how many bits of encryption are used for each of those various different algorithms that are used to be able to make cryptography work. So for the purposes of our demonstration here, I'm going to choose the Microsoft Strong cryptographic provider. It identifies which signing hash algorithm do I want to use. When a CA produces a certificate, that certificate gets handed over to somebody. That person can use that certificate to say, look, the CA says this is who I am. But that only is meaningful if the person who receives that certificate has some way to validate that that's true. We don't want to be able to be passing around the equivalent of fake IDs in the certificate authority environment. We want actual legitimate driver's licenses. Well, how do we do that? Well, how does a police officer validate that you've handed him or her a correct driver's license? Well, there are technologies built into the way that the license is constructed that a police officer can verify that are hard for ordinary people to recreate. Symbols that only appear under certain customized kinds of light, holograms, things of that sort. There are ways to authenticate that that certificate, if you want to think of it that way, the driver's license, came from an authorized certification authority, the Registry of Motor Vehicles. What's the equivalent in the CA world? Well, that's something called a hashing algorithm. I can take a large piece of digital data and run it through an algorithm that scrunches it down to some typically smaller piece of data. The smaller piece of data is a representative of the large piece of data in the same way that the Cliff's Notes summary of a piece of literature is a representation of the original. But like that same relationship, I cannot work my way back from the compressed, summarized version of that data back to the original. But what hashes are good for, although clearly not for compressing and uncompressing, what they're very good for is for digital identification of data. If I take a large piece of data and I run it through a hashing algorithm, what comes out is some small piece of data that almost certainly could only have been produced by the input of the original piece of data. If I run a piece of data through that same hashing algorithm that is even in the slightest different from the original piece of data that I used in my example here, the output hash is wildly different. Hashing algorithms deliberately produce dramatically different results, even for very, very similar inputs. And as such, the hash that I do end up with is kind of a thumbprint of the original data that I started with. When a CA issues a certificate to somebody, That CA is going to associate the hash with that certificate, and it'll encrypt that certificate using its own private key. Someone can validate that that certificate definitely came from the CA when they can decrypt it using the public key of the certificate authority, which of course everybody has because it's public. At that point, the current content of the certificate can be rehashed using the same hashing algorithm, and that rehashing can be compared against the hash that the CA supplied. If those hashes match, we know that that certificate has not been changed in any way. There hasn't been any damage to it. It hasn't been tampered with by somebody trying to trick us into thinking that there's somebody that they're not. So we get our choice of a number of different hashing algorithms: secure hash algorithm 1, message digest versions 2, 4, and 5. Again, our choice of which hashing algorithm is best for which purposes is a discussion best saved for another time. For our purposes, I'm going to choose the popular message digest 5 format, and I have an option to allow the ability for an administrator to be involved in a case where we're going to be doing any sort of work that's sensitive related to the private key associated with our CA. Having done that, I'm going to click Next. We need to supply some identification information about our CA. It's going to have an identification within the overall network. It needs a name. CAs are identified first and foremost by something called a common name. And in general, and by default, Certificate Services is going to choose a CA common name that embeds the name of the domain of which it's a part, if it's an enterprise CA, the name of the server itself, and the term CA. Now I could choose some other name if I chose to, but in many cases that's very neatly descriptive. It helps me locate that CA later. If I give it some clever, creative name, I might struggle later to try to remember on which server I had installed the CA. Beneath that is a description of a distinguished name suffix. A DN, a distinguished name, is an LDAP style name. LDAP is the underlying database structure that supports Active Directory. So we can see here that when we put all those pieces together, we end up with an object whose common name, the name of the individual server itself, is GlobalMantic's Dallas Server 2 CA. That server sitting inside of a container whose domain component is GlobalMantic's and whose other domain component is local. Or in other words, the globalmantics.local domain. What we're looking at here is a sophisticated Active Directory way of saying that this server is GlobalMantic's Dallas Server 2 CA dot globalmantics.local. That all looks fine. I'm going to click Next. The next question is, for how long will certificates generated by this CA be valid? Because these keys are protected by a strong asymmetric encryption, a public key infrastructure encryption model, I can deploy these certificates for quite some number of years without risk of somebody compromising those certificates and being able to misuse them. So I get to choose the amount of time. It might be some number of days or weeks if I want to be able to cut things down to renew that quickly. This calculation will be determined by things like, what's our current threat environment? How strongly are we likely to be attacked by the bad guys? If you're a large multinational corporation, probably a lot. You're a big target. If you're a small mom and pop shop, maybe you're less vulnerable. But in any event, we need to think carefully about the operating environment in which our certificate server is going to be doing its work. So in this case, I'm going to leave the default of 5 years and click Next. Certificate authorities store their information in a database, much in the same way that a SQL Server database does, or other database-driven applications like domain controllers. That database has to live in a particular location, as does the companion transaction log file. Many server-based database applications don't use just a single file to store their information, because for performance reasons, it's challenging to do all of our writing to the original database file. There's a lot of processing involved with accessing a database file. I need to gain access to the database file. I need to lock the portion of the database that I want to change. I need to make my change, release my lock, and disconnect from the database. That's a lot of work. So what a lot of database servers do, and the CA database is no different, is that it writes changes first to something called a database log. Now this isn't a text error log that you can read. Now this is a binary encoded summary of the changes being made to the database. Those changes are written to that file in that location, and periodically when the CA server isn't busy, it takes changes that have been written to the log file and commits them through a process called checkpointing into the main database itself. I might consider, for performance reasons on a heavily used CA, the idea of putting the CA database on one physical disk and the transaction log on a different physical disk. If I've got two different physical hard drives in my system, I can improve the performance of that system by doing that split. And the reason that helps is because when I want to go commit changes from the transaction log into the database, I can be reading from the transaction log at the same time that I'm writing changes into the main database. Those things can happen in parallel. Contrast that against the scenario where I've got the database and the transaction log together on the same physical hard drive. I can only read or write at any given time on that disk. So if I want to take a change out of the transaction log and write it into the main database file, I need to do a read and then a write, and then I can go get the next piece of data off the transaction log, read that data and wait, and then write and wait. The technical term for that is drive contention. I've got multiple processes contending for access to that disk that are essentially fighting each other for the ability to perform what tasks they have been asked to do on that drive. Multiple physical disks will definitely improve the performance of database applications of this sort. All that done, we're ready to confirm all the changes that we've made. I'm going to click the configure button and off it goes. So this next part of the video is going to take a minute or two here, but here's what I'm going to do. I'm going to push the magic train signal button, and this is now going to run much faster than it would in real life. And there we go. Now don't forget that I could have automated some interesting chunk of this installation if I had created a properly configured capolicy.inf file. And we're going to put that file at the root of the c:\Windows directory before I start the installation of the certificate authority. If I do that, the installation process will take up that file and apply the configuration settings that are in it. If I've got a large number of CAs to roll out, it's a great way to ensure consistency in the installation of all of those CAs. I definitely don't want to get to the end of a national rollout of a PKI and find to my surprise that one of my CA servers is acting very differently from all the others. Because by the time I got to configuring that one, I was getting tired and made some mistakes. Yikes. I can pre-configure, if you want to think of it that way, many of the interesting configuration settings of a CA in that capolicy.inf file. So again, by all means, review the documentation around how that file gets created. Search for capolicy.inf syntax, and you'll find it on Microsoft's Active Directory blog on the Microsoft website. I'm going to click Close here. I'm going to close up my Roles and Features wizard, and I now have a certificate authority. What do I do with it? Well, to be able to take a look at it, I can go to the Tools menu, and I now have a Certification Authority item in that menu. And there we are. The Certification Authority is up and running. It is ready to receive some set of pending requests, which it will process and turn into issued certificates. Unless, of course, that enrollment for that certificate fails in some fashion, in which case it becomes a failed request. Those certificates will be handed out to individuals, and we will urge them to be careful to safeguard their private keys, but inevitably some of them will inadvertently do something foolish with them and leak that information, in which case we'll then find those certificates and revoke them, and they'll drop into the revoked certificates container. And as we identified back at the first slide that described this CA process, those certificates are generated based upon something called certificate templates. And those certificate templates identify the kinds of certificates that are relevant to roll out in my environment. So I get a phone call from somebody who wants me to create a certificate for them. I've now got a tool with which to do exactly that. So I hope that gives you a good backgrounding in what a certificate authority is and why you would want to use one. And I look forward to sharing more with you about how to configure your CA and deploy certificates that will serve your organization's purposes in other lessons.